Welcome to the Explainer. Today, we're jumping into one of the most critical systems on our planet, the engine that drives all life as we know it, the carbon cycle.
Okay, let's kick things off with a bit of a riddle. What on earth do a sparkling diamond, the lead in your pencil, and, well, you have in common?
The answer, of course, is carbon. It is the ultimate building block of life. I mean, it makes up about half of all the dry biomass on Earth, and yep, that includes us.
All right, so here's our game plan for this journey. First, we're going to look at where all this carbon is actually stored. Then, we'll check out how it gets around. After that, we'll get into the difference between a carbon sink and a carbon source, a super important distinction. And finally, we'll tie it all together to see the big picture.
Okay, first up, the warehouses. Let's figure out where all this carbon is actually kept. Think of these as giant natural storage units scattered all over the planet.
So a carbon store is basically any place where carbon piles up and just hangs out for a while. Now, the average time a single carbon atom stays put is called its residence time. And this is pretty wild. It can be anything from a few days to literally millions and millions of years.
Okay, now check this out. This is where you really start to see the scale of these carbon warehouses. The atmosphere, it's holding about 750 billion tons. All the plants and animals on land, around 580 billion. But look at the oceans. They're holding a staggering 38,000 billion tons. Just incredible. But even the ocean gets dwarfed by the biggest warehouse of them all. This number, it's almost too big to comprehend. That's the amount of carbon locked away in sediments and rocks, like limestone. It just blows every other store completely out of the water. This is the super, super slow part of the cycle, the geological part, designed to keep carbon locked up and stable for hundreds of millions of years.
All right, so if those are the warehouses, how does the carbon travel between them? Let's take a look at the carbon highways, or what scientists call flows.
Now, this whole thing can seem pretty complicated, right? But let's start with the simplest version of the cycle. You know, the one you'd want to have down pat for an exam. It really just boils down to 3 key steps. Okay, here we go. 1. Plants breathe in carbon dioxide from the air through photosynthesis. 2. Animals get that carbon by, well, eating the plants. 3. That carbon goes back into the atmosphere when both plants and animals breathe out, or respire. Simple as that. That's the basic loop that keeps life going. Okay, now that we've got that basic loop down, let's add a couple more crucial highways to our map. These two have a huge impact, especially when you start thinking about longer periods of time.
First up, we've got fossilization. This is a slow process. We're talking millions of years. It's what happens when dead organic stuff gets buried without any oxygen around to break it down. Over eons, all that pressure turns it into things like coal and oil, which basically just locks that carbon deep, deep underground.
And then on the complete opposite end of the spectrum, you have combustion. Unlike fossilization, this is an incredibly fast process. When we burn these fossil fuels, we're taking all that carbon that was stored away for millions of years and poof, we're releasing it back into the atmosphere in what is, geologically speaking, the blink of an eye. Okay, so this brings us to a really crucial point, the balance sheet. It's all about understanding the balance of carbon moving in and out of these stores. Think of it like a planetary bank account with deposits and withdrawals. It's actually pretty straightforward. If a store takes in more carbon than it releases, we call it a carbon sink. But if it releases more carbon than it takes in, we call it a carbon source. Sink versus source. Got it? Let's make this real with a forest. A young, growing forest is full of trees that are just sucking CO2 out of the air like crazy to grow bigger. They're in major growth mode, which makes the whole forest a really powerful carbon sink.
But what about a stable, mature forest? Well, it's a bit different. The carbon it's taking in for new growth is pretty much balanced out by the carbon being released as old trees die and decompose. It's reached a kind of equilibrium, acting as a massive, stable carbon store, but not necessarily a sink.
And now for the flip side. What happens if that same forest burns down or gets clear-cut? All that carbon that was locked up in the trees gets released, and fast. The forest instantly flips from being a stable store into a major carbon source.
All right, let's zoom out and put all these pieces together. Seeing the big picture is really the key to understanding why this whole cycle is so incredibly important for keeping our planet stable.
So here's the bottom line. The amount of carbon on Earth is finite.
It doesn't just appear or disappear. It's just endlessly recycled through all those warehouses and highways we talked about, providing the literal building blocks for every living thing. And this quote really says it all, doesn't it? Elements such as carbon are not limitless resources. The carbon we have is all we've got. The whole system of life on Earth depends on recycling it over and over again. Which leaves us with one last really big question to chew on. For ages, this cycle has kept Earth's climate in a pretty stable balance. So what happens when you take one of those key flows, combustion, and you suddenly slam your foot on the accelerator, massively speeding it up? What happens when you take carbon from a million-year storage unit and dump it into the atmosphere in just a couple of hundred years? That's something worth thinking about.